For our in-class lesson, we decided to focus on the concept of drag. The main objectives of this presentation are to introduce the audience to the concept of drag, mention and explain the different components of the total drag force, as well as explain some of the ways that they are calculated, and show some solutions engineers have developed to reduce drag forces. We will start by defining drag. Drag is a mechanical force. This means it is created only by physical contact. It is generated by the interaction of a solid body with a fluid. Since physical contact is vital for this force to be created, if there is no fluid, there is no drag. There also must be motion in order for drag to be generated. A static body on a static fluid will not experience any drag. For our purposes, air will act as our fluid and, unless otherwise specified, the wings of a regular, commercial aircraft will act as our body.
There are three main types of drags. The first type of drag is parasitic drag, which is divided into interference drag, form, also called shape drag, and skin friction drag. The second type is induced drag, and the third type is wave drag. On this presentation, we will focus on aircraft cruising at subsonic speed. Therefore, we will give more importance to the first two drags. As we move on, we will explain why wave drag is less important for our purpose.
Parasitic drag. The parasitic drag of a typical airplane in the cruise configuration consists primarily of the skin friction, roughness, and pressure drag of the major components. There is usually some additional parasitic drag due to such things as fuselage upsweep, control surface gaps, base areas, and other extraneous items. Parasitic drag is a combination of form drag, skin friction drag, and interference drag. It is important to mention that parasitic drag is sometimes defined as all drag not associated with the production of lift, which means that its minimization or elimination do not affect the aircraft's ability to fly. Interference drag is just the mixing of airflow streamlines around two different components of the aircraft. For example, streamlines coming from the wings close to the fuselage would mix with streamlines coming from the fuselage. Since the two airflows must share the same space, the competing airflows must speed up to pass through the restricted area, created turbulent flow. This turbulence also creates an increase in form drag.
Form drag is defined as aerodynamic resistance to the motion of the object through the fluid. This source of drag depends entirely on the shape, velocity, and angle of attack of the aircraft. Since the fluid flows around the body, there is a constant change in pressure and velocity in every single piece of the body. Since pressure is measured with the momentum of the fluid's molecules and force is defined as changed momentum, the magnitude of this force can be calculated with the following formula. F form equals C form times rho times U squared over 2 times A. C form is the drag coefficient. This coefficient is a dimensionless quantity and it is totally dependent on the shape of the body. This coefficient is used to quantify the resistance of a body in a fluid environment. Although there are formulas that determine this quantity, it is usually determined experimentally. A low drag coefficient means low resistance and therefore low drag. Here are some values of C form for some common shapes. Notice that the round shapes represent the lowest coefficients, whereas the flat ones generate the highest resistance. Rho is the mass density of the fluid. At standard pressure and temperature conditions, the density of dry air is 1.29 grams per liter. However, this value depends on many variables. For example, the altitude at which the aircraft is flying determines both the temperature and pressure factors, which define the value for the mass density. U stands for the relative velocity of the fluid to the aircraft. The subscript infinity means that this measurement is made infinitely far away from the aircraft. This value usually accounts for the speed of free stream that has not been disturbed by the aircraft. Finally, A accounts for the area of the wing. This area is usually thought as the frontal area of the body, and in most cases it is equivalent to the cross-sectional area. For example, let's assume that the body is a sphere. The value for the area in the form drag equation will be equivalent to pi r squared, the cross-sectional area of the sphere, rather than the surface area of the sphere.
The boundary layer of an aircraft wing is the area of airflow that is extremely close to the wing where the effects of viscosity become significant. Two different types of flow occur in the boundary layer: laminar and turbulent flow. Laminar flow is parallel to the surface of the wing and is very smooth, whereas turbulent flow contains many swirls and often results in much more skin friction drag. However, laminar flow is much more difficult to maintain and is unstable. Therefore, once the air travels far enough down the surface of the wing, the flow will become more turbulent, resulting in more skin friction drag. Drag can also be thought of as a result of aerodynamic friction. Skin friction drag is generated by the friction created between the fluid and the solid body. The magnitude of this frictional force is also dependent on the properties of both elements. Thus, a smooth and waxed surface and a fluid with little viscosity would yield a low skin friction drag force. The magnitude of this force can be calculated by using the following formula. Skin friction is equal to 0.664 rho nu squared S sweat divided by the square root of Rn. Rho is the mass density of the fluid. Also, it is the same as in the form drag equation. Nu is the velocity at which the fluid flows across the surface of the body. Rn stands for Reynolds number. The Reynolds number is dimensionless, and it is used to quantify the viscosity of a fluid. It is determined by the formula Rn is equal to nu L divided by V, where nu is equal to the velocity of the flow, L is the length of the body, and V is the kinematic viscosity of the fluid. The viscosity of the fluid varies depending on pressure and temperature factors, such as the mass density. Here are some values for the kinematic velocity of the air. Notice that the viscosity of air gets significantly higher as it approaches high temperatures. S wet is simply the surface area in contact with the moving fluid. Notice that this time we are using the surface area of the body and not the cross-sectional area as in the form drag equation. In order to reduce parasitic drag, engineers have developed different solutions. For interference drag, appropriate use of fairings and fillets between the main components of the aircraft have shown to ease the transition of the flow coming from the different components. For form drag, minimizing the frontal area of the body and using shapes with low drag coefficient will minimize the drag force. For skin friction drag, smooth surfaces, along with special coating and waxing, has been shown to ease the flow of the fluid along the surfaces.
The second main type of drag is induced drag, also called drag due to lift. It is produced by a difference between the pressure on the top and bottom surfaces of the wing. This pressure difference is greater at the wingtips, where a swirling flow, responsible of the drag force, is created. Induced drag depends on many variables, but it is mainly affected by the amount of lift that is being produced. Induced drag can be calculated by using the following equation. D equals 0.159 L squared over rho mu squared S E A R. L is the lift force, the force that directly opposes the weight of an airplane and holds the airplane in the air. This force can be determined by the following formula. L equals CL times rho V squared over 2 times A, where CL is the lift coefficient, a number that aerodynamicists use to model all the complex dependencies of shape, inclination, and some flow conditions of lift. This number is determined experimentally. Rho is the mass density, same as in the previous equations. V is the velocity at which the aircraft is traveling, and A is the area of the wing. Rho is the mass density of the fluid. Mu is the velocity of the flow. S is the surface area of the wings. E stands for the efficiency factor. This number, also known as the Oswald efficiency factor and sometimes referred as the wingspan efficiency factor, is the ratio of the amount of lift generated by the wings over the maximum theoretical value. This efficiency factor is based on the lifting line theory of Prandtl, which states that the maximum theoretical value is the amount of lift generated by perfectly elliptical wings. Based on this theory, it can never be greater than 1. However, it is still matter of study and has not yet been determined whether the maximum theoretical value is truly that one produced by elliptical wings or not. Finally, AR stands for the aspect ratio. The aspect ratio is defined as the wingspan square over the wing area. This value is dependent on the size and shape of the wing. Here are some solutions to reduce induced drag. The use of an elliptical wing will create the best efficiency factor, giving away lower induced drag. Folded wingtips are used to change the direction of the flow in the wingtips and avoid turbulent flow from forming in this area. Twisted wings are designed to have a higher angle of attack at the base than at the tips, which simulates the effect of an elliptical wing. Lastly, wing fences block airflow around the wing and prevent the wing from stalling all at once.
The last type of drag, and the least important for our purpose, is wave drag. Aircraft flying at subsonic speeds do not experience wave drag. However, an aircraft traveling at supersonic speed generates pressure waves as it moves. These pressure waves accumulate and turn into big shock waves, which alter the pressure distribution along the surface of the aircraft. This change in the pressure distribution generates high drag and slow down the airplane. There are a couple ways to reduce wave drag. Thin objects reduce the accumulation of Mach waves, which creates less strong shock waves and therefore reduce the drag. Applying the area rule also reduces this type of drag. The area rule implies that there should not be any abrupt change in the cross-section area along the longitudinal axis of the aircraft, because the wave drag is proportional to the change in that cross-sectional area. Sweep wings essentially act as if the wing was thinner by reducing the thickness to core ratio. Also, they decompose the flow over the wing into components, which reduce the flow's speed.
Test your understanding. How would you describe drag? Which of these statements are true? Which type of drag is dependent on the shape of the airfoil? How can we reduce induced drag?